Hello, this video is on vector fields, looking at paths that vectors take and what kind of applications can we get from that. And like this is called an airflow field. You can see how it would flow over the path of that vehicle. And the next one's a gravitational field. And being gravitational, you can see how the vector function is all heading inward. So let's look at the definition of a vector field. Now, whether it's plane or space, here, x, y, z, it's kind of the same thing. So I'll just deal with the bottom because the top one just doesn't have a p in it. So, all right, so suppose that, f's a function of x, y, and z. So the vector field, we use capital F notation for vector field, means that you'll have m, n, and p are components, functions of x, y, and z, and they each go with I, j, and k. That's what makes them a vector field. So like, this one could be x squared I plus, it doesn't have to be the order either. You can mix them up like you'll see here, and you could have y, z, j plus x, z squared, k, or something like that. Now, of course, we can write these in component form. They don't have to be in standard unit vector form. Now, I'm not too concerned about having you plot any of this. I just kind of wanted to have you take a look at it. And here's one that's not supposed to necessarily have any kind of physical meaning, like the ones I was showing you above. And to plot vectors, what you do is you pick points. You pick a point, and then when you plug it into the vector field equation, it generates a vector from that point. So 1, 1 generates, you put in 1, 1, you'll get 1i plus 1j. So you come over here, and let me change the color of this. Oh, that's no good either. You start here at the point 1, 1, then you draw the vector up 1, over 1, and up 1. So that's the 1, 1 vector. And then I'll just skip this bottom one. So at 2, 1, you put 2 in there, you get 2 squared times 1 is 4. 2 times 1 squared is 2. You get the vector 4, 2. So at the point 2, 1, the vector stemming from it would be 4 and then up 2. And I used maple to graph this vector field. Now what apparently the maple's doing, I'm assuming that these are probably unit vectors, which kind of makes sense that it's a unit vector. In other words, just to kind of give you an idea of the pattern. In other words, I was actually drawing the full length of the vector. But if you look at these, they're all the same length. So they just took them and probably just made them unit vectors. So they didn't do one at -1, 1, so I can't use that as an example. But let's look. Okay, let's look at this one. At -1, -1. I must have plugged a few more in there. Oh, here they are over here. This one, -1, -1. Yeah, see, it goes down to the left like that, just like this one does. And then at -2, -1 is this one right here. It's a little flatter than that one, just like this one is. Like I said, it's just not as long as the one I drew by hand. So that's the nice little thing that Maple does. It shows the array of the vector field here. And you can see the ones that are in quadrant 1 are all going away from the origin. All right, so I just kind of wanted to get you, and of course, space would be really too hard to draw these. So without having you to actually graph them, I just kind of want you to get a feel for what's going on here. Oh, here's a three-dimensional one. Looks like I decided to make these, I was playing around with the settings and decided to make these vectors extra thick for some reason. Yeah, I put thick, I don't know why, but made it make it look more powerful. But this was a function that I got out of a textbook that was supposed to represent a gravitational field. I got that out of a book. So, and then sure enough, yeah, I wouldn't have known what to put in there otherwise. But sure enough, look at the pattern of the vector field. They're all heading inward toward the origin. So it kind of makes sense that that's a vector field. Now, I don't know what I did over here. This must be a different one for a different problem. I don't know, because it doesn't look like it. Yeah, obviously it's not this one. That must be for something coming up here. Do I have a second vector there? It doesn't look like it. because obviously it's a space vector. So I don't know what that's what that second one was there for. I don't know. Maybe I accidentally deleted something. I'm going to take one more quick look here, and then I want to not obsess over it anymore. Oh, okay. Well, all right, I'm sorry. I should have seen that. Never mind. You probably already figured this out by the time I did here. But all right, so I didn't actually write the function. Okay, I did the same thing. I just typed in another random vector field there, x, negative y, z, and then that's what it was. Okay, so sorry about that. Yeah, so that gravitational field is this one right here. Now we have something called a conservative vector field. A vector field is called conservative if there exists a differentiable function f such that the vector field fxyz equals the gradient of your what's called this function f, which this function f is called the potential function. So if it has such a function f where you can take the gradient of it to yield that vector field, then it's called vector field is conservative. So not every one of them will have it, and we're going to see how to test for it here in just a second. So that some will have it, some will not. So and you should recall the gradient, where you take the fx partial, fy partial, and the fz partial, and they go with I, j, and k. So that's still the same idea as before. So let's look at this one. This one was designed to actually work here for the first one. So I'm saying that because I'm making it work because I'm just making up a function and then taking its vector field from it. So take x cubed y squared plus 2xy4, and I take the gradient of this, which would be the vector field. Yeah, that respect to x here would be 3x squared y squared, and then it'd be 2y to the fourth. And this one's going to be 2, bring down that, makes that 2x cubed y, and then 8xy cubed j. So the way we would be doing is we would be looking at this vector field below and seeing if it's conservative and then finding out what that function is right there. But obviously, that's not the way I did it here. But I just want to kind of show you the idea. So then we would call little f the potential function for that vector field, and the vector field would be conservative. I forgot to write that down there, but now here's how you test. Now it's going to be a little bit different for so this is going to be different for space vectors than for plane vectors. A lot of stuff we've done in this class, where it's 2-dimension or 3-dimension, a lot of times the same rule applied, but not in this case. So if you have a vector field in the plane, written, denoted by mi plus nj. So if you take the partial derivative of n with respect to x, and then the first one, m, with respect to y, if they equal each other, that means you have a conservative vector field and you will have a potential function. So now I'm looking at that last problem and the one I kind of made up so it would work. Now we're working it backwards, or more like, normally what we would be doing. We would have this vector field, and we would be determining, can we get a gradient function, a potential function from there. So you look at this, and then here's the n right here. The n's the one that goes with j. So we're taking the partial derivative of n with respect to x. So that will be, bring the 3 down, it'll be 6x squared y plus 8y cubed. And then my, right here, the first one, with respect to y, will be 6x squared y plus 8y cubed. So see, they equal each other. Nx partial equals the my partial, so that means there would be a potential function, which we already know what that one's going to be for this problem. Now we're going to solve one on our own here in just a minute. But obviously that's going to be, we're going to see how to get that here in just a minute. But I didn't do it for this one because we kind of already have it. So we'll do a fresh, shiny, new problem here. Well, here's one that, okay, first of all, determine. So usually let's say if it's, determine if it's conservative, and then if it is conservative, find the potential function. Well, this one, so we'll test this. So the nx right here would have a partial of 12x cubed y. My would be, bring the 3 down, be 3x squared y squared. So it's not conservative, meaning there's no potential function f whose gradient's going to equal this vector field right here. Well, okay, I guess I kind of spoiled the conclusion for this one. So it's, yeah, it's already telling you it's conservative, but I did check to verify. So nx right here, this partial, 4 times 1/2 is 2. It'll be 2x cubed y. And then the my partial, bring the 2 down, it'll be 2x cubed y. Conservative. Therefore, we do have a potential function to find. So what we do is, because this potential function is coming from the gradient, which the gradient is a derivative that produces the potential function, we'll take the antiderivative, the first term, because it was found by taking the derivative of x, then we will integrate m with respect to x, and then we'll integrate n with respect to y. So let's see what we have here. Let me scroll back up here, see if I can get all this in the picture here. Okay, well anyway. Well, I wrote it. So there's your m component right here, and the one below it will be the n component, so you can see it. So the antiderivative with respect to x, so that'll be x3 will be 1/4 x to the 4th y squared, minus the antiderivative of this is 2x squared. Now the bottom one, antiderivative with respect to y. So y will be 1/2 y squared, so it makes it 1/4 x to the 4th y squared. And then the antiderivative of 6y with respect to y will be 3 minus 3y squared. Now here's how you come to the conclusion. Now you're going to have, every time you're going to reach one that has in common, it could be a little more involved. It may be the only thing you have, actually, but this one I intentionally created a problem where it had extra terms, just so you can see. But you're always going to have that one common one between the two. So what you do is you include the common one only once. It only has to be in there once, and then any individual pieces go in there with it. So we include these two things only one time. So the potential function is going to be 1/4 x to the 4th y squared minus 2x squared minus 3y squared plus c. A lot of times this book uses plus k, which is still a constant, but I guess they're trying to distinguish it from the normal plus c. And if we're not sure, we could just see we got it right. I'm not going to work all that out, but I'm saying, it's easy enough. Just check the gradient of this function right here. Find the x partial and the y partial, and then it needs to equal our vector field. And it does. So if you take the gradient of this, you will get our vector field right here. So that's the surefire way to know that it's correct. All right. Same kind of thing here. Let's look at this one. So nx right here, that one, I can do my first, whichever one, doesn't matter. Nx is going to be 6x squared y. For some reason I've been doing that one first, but if you did my first, no problem. My, bring the 2 down, 6xy, they equal each other, so it's conservative. So you take the antiderivative of the first term, the m term, with respect to x. So the antiderivative of 3x squared will be x cubed along with the y squared. The bottom one, antiderivative of n with respect to y. So basically y will be y squared over 2, and the 2's will cancel. You'll get x squared x cubed y squared, no other loose term. So you see this one, so you're going to have that common connection for sure, and some possible other terms that would need to be included. So since we only have that one common term, then that term is our answer. So the potential function f of xy will equal x cubed y squared plus c. Now here's how we're going to deal with conservative vectors in space. We're going to learn a calculation here, which obviously you can put this on a formula sheet so you don't have to memorize it. The curl of a vector field of f, x, y, z, see has three components. And there it is kind of written in that partial derivative notation, but I just kind of shorthanded it here, the other acceptable way to write it. So it's kind of like, actually, if I would have shown it formally, it's like a cross product, basically. But I didn't write that out. But that's okay, because you don't really need to. You just need this. So it's py minus nz, and the middle term will be mz minus px, and then you'll have nx minus my. Okay, so when you find the curl, sometimes you can find the curl like we've been doing, not curl, but we've been finding stuff that you can an algebraic form like this. But then if it gives you a point, no problem. That just means you plug the point in and you'll get a numerical vector answer in that case. So that's all. So you would just take it one step further from that formula and just plug the numbers in. But let's get the curl in now algebraic form first. So I wrote down, so it's py minus nz. So p is the third term. So the derivative of yz with respect to y will be z. And we have minus from the formula nz. Don't forget when you have subtraction here to include that anywhere, use a negative. Include that negative with it. So the derivative of n respect to z will be negative 2x. So actually it's z minus a minus 2x. Then we have mz. This partial derivative will be x squared minus px. There's no x term there, so that's going to be 0. Now we go to the third component. nx, once again, include the minus. So the derivative of 2xz will be negative 2z with the negative, makes it negative 2z. And then my will be 0. So you end up with the curl will be the vector z plus 2x, comma, x squared, comma, negative 2z. So like I said, if it was not asking it at a point, we'd be done. But it wants 2, negative 1, 3. So I didn't show a lot of work for that, but just obviously everywhere there's an x, plug in 2. Everywhere there's a y, there's no y's there, plug in negative 1. And then everywhere there's a z, plug in a 3. So it's a matter of just plugging and chugging. So the first one would just be 3 plus 2 times 2 is 7. Second one will be 2 squared is 4. And the last one will be negative 2 times 3, which is negative 6. I think I did a curl, yeah. Let me see, okay. All right, so there we have it. Now let's look at the next topic. So let's take a look at this theorem, how to test for conservative vector field in space. And as I mentioned earlier, this would not be, it would be a completely different method than it was for testing it in plane, where you had the nx equals my partials. Well, it's real straightforward. Well, maybe it's more tedious. The other one's also straightforward, but it's a little more tedious. You have to calculate the curl. And a vector field in space is conservative if and only if the curl is the 0 vector, meaning you get 0, 0, 0 when you perform the curl. So that's basically it. Now, of course, it's showing you these you can do it this way if you want to, obviously, because that's also going to be true. Because if you look back up at this formula, like right here even, if that's going to be 0, obviously that means py has to equal nx, mz equals px, and nx equals my, so that's obviously true. Okay, so let's look at this vector field, and then we'll talk about finding the potential function for the vector field like we did in the space, like we did for the plane. So here, look at this example right there, and let's crank it out and see what happens. So py minus nz, py minus nz. So this partial with respect to y, bring the 2 down, 6xyz squared, and nz, bring the 3 down, makes that 6xyz squared. Okay, so far so good. So we got 0 for the first one. So obviously if any one of them is not 0, it's not conservative. Let's do the middle one. mz minus px. So mz, bring that down, would be 3y squared z squared, right there. Px will be, x goes away, derivative is 1, so it's 3y squared z squared. Okay, we're 2 for 2. But, don't assume that's the first 2 means you're going to get the third one. Well, you can in this example because I already have the answer there, but in general, don't assume, well, I got the first 2, so, third one's bound to be true. That is not correct. And so let's see what we have here. nx minus my. nx will be 2yz cubed. And my will be, bring the 2 down, 2yz cubed. So we have it. It's conservative. And we have a potential function then whose gradient will then equal that vector field. So this just expands one more variable to what we were doing before. So we still integrate the m1 with respect to x, the n1 with respect to y, and now we integrate the p term with respect to z. So those are all coming from right back here. 1, 2, 3. So we integrate those with respect to the different variables. So let's see what we have. So y squared z cubed respect to x is x y squared z cubed. 2xy z cubed respect to y, so 2y has an antiderivative of y squared. So you have xy squared z cubed. And the last one, integrate this term respect to z, so the antiderivative of 3z squared will be z cubed. So I have x y squared z cubed. They're all the same. So now, when you have 3 of these, here's what can happen. In this case, they're all the same. We only include them once. So if you have 3 like terms, include them once. If any 2 of the 3 are like terms, include them once. And then any other all straggler terms you include with it. But that one just had one common term. So the key is that 2 of them can be alike and you still only write it once. It doesn't have to be all 3 of them. And then I just put a check mark there. I probably mentally checked that gradient. I didn't actually work it out, but that's a good exercise for you if you want to take this gradient and find it and make sure it equals the vector field. Now we're going to learn another term here. Okay. Finding the divergence of a vector field. Now that's going to be a scalar quantity. Now you see I just copied the same formula twice and just eliminated the last term for the plane. But this is one where it's done kind of the same way, plane or space. You just have one term. So it's 3 partial derivatives added together. It's the m component of the vector field with respect to x plus the n with respect to y plus p with respect to z. So let's take a look at this. Now you see these are given at points, but it doesn't have to be evaluated at a point. The divergence can just be a scalar function of x's, y's, and z's. It can have an answer of x, y's, and z's, but it just won't be a vector. In other words, you could have an answer that was, 2xz plus y squared. That's not a vector, but that would be the answer. All right, so the divergence of this example, so derivative mx here, x would be 2xz. The middle term, the derivative of y is 0. And then the derivative of yz with respect to z would be y. So really you have 2xz plus y would be acceptable as a divergence, but now they want to evaluate it at a specific point. 2, -1, 3. So you just plug in, remember, 2 for x, 3 for z, that makes that 12. -1 for y, 12 minus 1 is 11. Now this next one, I kind of used log properties here to make this a lot simpler. So I broke up the natural log of x plus y, x, y, z as natural log of x plus natural log of y plus natural log of z. Now that might be a little weird the way I wrote this here, but let me explain that this does not mean you're really multiplying a trinomial times a trinomial. That's sort of what it looks like mathematically, but no, it's just ln of xi, ln of yj, and ln of zk. You see how they wrote that there, so I could have distributed that out, but that's okay. I don't think it's too bad, but I want to at least verbally explain that since it wasn't written. So derivative of ln of x respect to x, 1 over x. Ln of y will be 1 over y. Ln of z will be 1 over z. And then our point this time is 3, 2, 1. So you have 1/3 plus 1/2 plus 1 over 1 equals 11 over 6. So let's take a look at this example. Divergence, just in terms of x, y, and z. Then we'll put in 0, 2, 0. Okay, this was kind of interesting. We got an e in there and got a sign in there. Good chain rule practice. So the derivative of the first component with respect to x will be 3e to the 3x times y squared. The middle one with respect to y will be the derivative of y cubed will be 3y squared. So I have 6x y squared z to the fourth. And the last one, another chain rule here, got to take the derivative of the 2. So the derivative with respect to z makes that 2 cosine of 2z with the y cubed there also. But you see how I wrote that? Just plus, 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 not a vector. All that right there is perfectly good answer for divergence. Now I plug 0, 2, 0 in there. I trust you can do that, okay? E to the 0 is 1, don't forget. Cosine of 0 is 1. So I end up with 28. Now I guess I'll do the div of the curl. We'll have to walk through the curl. So let's find the curl, which we can do as py minus nz. I think I'll copy the original function down here so we can see it, vector field function. And I'll probably delete it. Put this where we can at least see it right here for a moment, momentarily. There it is. So py, the last term with respect to y, will be 3y squared sine of 2z, minus nz, the middle term with respect to z, bring the 4 down, 8x y cubed z cubed. Middle term mz, first one with respect to z, no z, 0, minus px, the last term has no x, so 0 minus 0. So just to let you know, the first, that means already this vector field's not conservative. The question wasn't asking that, but I just wanted to mention that. And then the last one will be nx. So it'll be 2y cubed z fourth minus the my. First one with respect to y will be 2 e to the 3xy. Now the div of that curl, we would take the derivative of this first part with respect to x. So there's no x here, so that x goes, and we keep the negative, so x goes away to 1, so it's negative 8y cubed z cubed, middle term 0. The last term respect to z, there's no z here, so it's just this one, 2, 8, so 8y cubed z cubed, have 0 in there. Add those together, we get 0. So was that some sort of fluke? Actually, it is not a fluke. So actually, anytime if you were just asked to find the div of the curl, you don't even really have to do it, because the div of the curl automatically equals 0 every time. And that concludes the video for vector fields.